Download this code from codegive.com, link in the description below. UART interrupt with user callbacks on stm32, episode 13. In this tutorial, we will explore how to use UART interrupts on stm32 microcontrollers and implement user-defined callbacks to handle incoming data. This approach allows us to create efficient and responsive applications by offloading tasks from the main program loop. Overview of UART and interrupts. UART, Universal Asynchronous Receiver/Transmitter, is a communication protocol used for serial communication between devices. Using interrupts allows the microcontroller to respond to data received on the UART interface without continuously polling the hardware, which can save CPU resources and improve performance. Prerequisites. Basic understanding of stm32 microcontroller architecture. Familiarity with stm32 development environment, example stm32 Cube IDE. An stm32 microcontroller board with UART capabilities, example stm32F4, stm32F1. Step 1, Setting up the project. 1. Create a new stm32 project. Use stm32 Cube IDE to create a new project for your microcontroller. 2. Enable UART. In the Cube MX configuration, enable the UART peripheral you want to use, example Uart 1. Make sure to configure the parameters, baud rate, word length, stop bits, etc., according to your requirements. 3. Enable interrupts. In the configuration, enable the interrupt for the selected UART peripheral. 4. Generate code. Click on the Generate Code button to create the project files. Step 2, Write the callback function. In this example, we will define a callback function that handles the reception of data via UART. 1. Open uart.c. In the core/src directory, open the uart.c file generated by CubeMX. 2. Define the callback function. Add the following code to implement a user callback function to handle received data. C. Include uart.h. Include string.h. Define buffer_size 100. Char rx_buffer // buffer for received data. uint8_trx_index equals 0, / index for the buffer. Void hal_uart_recapituled callback, uart_handle_type def *wart. / this callback is called when half of the reception is complete. / we can process the data received so far. Void hal_uart_recapituled callback, uart_handle_type def *wart. / this callback is called when the full reception is complete. / process the received data. Process received data, rx_buffer, rx_index. rx_index equals 0, / reset the index for the next reception. Void process received data, char *data, uint8_t length. / handle the received data. / for example, echo it back or parse commands. hal_uart_transmit, and word 1, uint8_t*, data, length, hal_max_delay. Step 3, Configure the UART reception. We need to configure the UART to receive data in interrupt mode. This typically involves enabling the reception and setting up the buffer to store incoming data. 1. Initialize UART reception. In the main program, example main.c, initialize the UART reception in a loop or in the main function. C. Int main, void. hal_init. Systemiclock_config. mx_gpio_init. mx_uart1_uart_init. / start UART reception in interrupt mode. HAL_UART_receive_it, and ward1, uint8_t*, and rx_buffer rx_index, 1. While, 1. / main loop can perform other tasks. Step 4, handle reception in the callback. In the HAL_UART_explt callback function, we use a buffer to store incoming data character by character. When the buffer is filled, or a certain condition is met, we call the process received data function to handle the received data. Step 5, compiling and testing. 1. Build the project. Compile your project in stm32 Cube IDE. 2. Upload to the board. Flash the program onto your stm32 microcontroller. 3. Test the UART communication. Use a serial terminal, like PUTTY or TerraTerm, to send data to your stm32 board and observe the responses. Conclusion. In this tutorial, we learned how to set up UART communication with interrupts in stm32 and use user-defined callbacks to process received data. Using interrupts allows for efficient data handling, while callbacks provide flexibility in how we respond to incoming data. This approach is essential for building responsive embedded applications. Feel free to modify the process received data function to implement your specific application logic, such as parsing commands or controlling peripherals based on the received data. Happy coding!